This is the final week of this quarter of instruction, that is. Next week is going to be final week, so it's really the last opportunity for us to kind of, do the last bits of studying before we have to go back to the auditorium to do another test. Okay, so today I'm going to cover the last bit of information of this course, and that means that Wednesday's lecture and Friday's lecture are review sessions, in-class review sessions, in which I will go through, again, a couple of points of interest, point out some general mistakes people make, and hopefully get you up to speed for the final. The final is going to be on December 14th. It's 2 hours, okay? It's a 2-hour exam. And the exam is going to be a little bit longer, but not twice as long, so less than twice as long. That means you have relatively much more time for the final, and just some people were asking questions about this, about time issues. There is no time issue on the final. There's plenty of time to finish all the questions. Most people hand in their exam before time is up. So the auditorium will probably be half empty by the time you call off the exam. Okay, so we had a midterm last Friday, and that was, that was an interesting experience. So let me show you how well we did all together. Let's see if this works. Oops. Yeah, there we go. This is the performance. It's really interesting. It's really all over the map. So it's a huge distribution. The mean is really in the middle, 52. Last year's was 56. This year's 52, so it's somewhat similar, a little bit lower. The exam was a little shorter this year relative to last year's. The distribution is 23. That basically means there's a huge spread. This 23 simply means how broad a distribution is. It's a broad distribution. Interestingly, also, it has all these spikes, and I have no idea where they come. I can't explain that. It's very untypical. Usually it's a rather smooth distribution. This one has all kinds of peaks, and you guys did something very amazing from that perspective. This performance is just incredible. Some people had lower scores in this area here. Some people had high scores. One person 100%, everything right. Very nice, congratulations. Nice. Yeah. Person may even be here. Person probably doesn't need any lectures. So most of the people are like here in the middle. If you are in this segment, so I would say below 30, then there is reason for really focusing very specifically on things that you want to improve on. Okay, because if you are in this area, there's really no, I would say. If you after two midterms are still in this area, that tells you a story that you are not fully up to speed to ace the exam. Let me put it like that. Okay? It doesn't mean that that's your lost case. Absolutely not. Midterms are meant to practice, get used to the material, get up to speed, see for yourself where are the problems that you have, and what are the things you have to improve on. That is what the midterms are for. The final is really the place where you have to show, how you have to digest it and process the information in the course. It's almost 50% of your grade. The final is really where it's at. Midterms are preparation for the final. Okay? So if you didn't do well in the midterm, that doesn't mean you have flunked the class. Absolutely not. It means you just have to focus on those things that didn't go so well. Sometimes not doing a midterm so well is actually not a bad thing, because it tells you very precisely where are the issues that you need to focus on. Okay? And so I'll say a few words about that in a few moments. There's lots of comments about the time issue in the exam. We have 50 minutes in principle, typically less, because we have to get started, hand out the exam. You cannot put the exam with one chair because we have less than 200 people here. so we don't occupy all the seats. So we have to hand them out on the spot, takes time, and try to do it as fast as we can. So we cannot use the full 50 minutes. I was trying to go a little bit over time. 52, everybody had to kind of basically hand in their exam, so we had a little bit of flexibility there. But basically, in less than 50 minutes, you have to show us what you can do. Now, it is fully understood, and I know that very well, that it is sometimes hard to complete all the questions. Okay? We are all in the same situation. Everybody is in the same situation. The time constraint is annoying, but it is somewhat part of doing an exam. Okay? There's always a fixed time of exams, and in chemistry it's no different. We have to test a bunch of topics, concepts for me to see where you guys are at in your understanding. Right? So if I just put 1 or 2 questions on the exam, you may be able to finish them, but what if you mess one up completely, you still have 50 points. Right? Now I spread it out over more questions, and you have a chance to show us what are the questions you can do well. You get full points for that, because you can demonstrate that. And then the questions that don't go so well, you lose points on. Also because you probably don't have time to finish them. Right? So shorter exams are not necessarily better. In practice, we have seen that shorter exams actually lead to lower grades. Because if you mess up a question, it's going to cost you dearly on shorter exams. Longer exams have that advantage. You can spread out your capabilities over more seconds of the exam. Okay, so please understand that. Secondarily, like I said, the time is not an unimportant factor. Okay? These calculations may be new to you, or maybe you've done it before, but you have to be able to do them in a certain amount of time. Okay? We don't have 2 hours or 3 hours for an exam, and in practice, if you are in the lab and your advisor asks you to make a solution of X many chlorine atoms in solution, a certain molarity, you should be able to do that in a couple of minutes. It shouldn't take you 10 or 15 minutes to figure out how many of these chlorine atoms are in there. I mean, no, you just kind of write it out, okay, and just be able to quickly translate that. This is a skill. We need to have those skills. So time is a quantifier, okay? It shouldn't take you an hour to determine what the concentration of chlorine ions are in an aluminum chloride solution. Okay, so let me give you 2 quick snapshots of the exam that we had last Friday, and just to highlight a couple of points that went wrong for about 50% of the time. Okay, this is the first question, question 1. A sample here, this happens to be version B. There is a molecule here, there's a molecular formula, and it says it contains 4 grams of carbon. Okay? It says it contains 4 grams of carbon. You've seen those questions before. Okay? You have this specimen here. It contains X grams of oxygen, of the element oxygen, or the element carbon. Okay? The question here is, question B in this case, how many moles of this stuff do you have? More than half of you did this. Okay, 4 grams divided by the mole mass of this. Okay, and most people actually calculate this correctly, which is good. Is this many moles? Unfortunately, that is not what this question is telling you to do. Okay? Read the question. I mean, just take a little bit of time. Don't think it's going to be too straightforward. Okay? We have had questions like this where an element is being specified. In other words, you know how much carbon, how much C there is, but you don't know exactly how much of the total compound there is. So you have to relate the amount of C to the amount of the total compound. This is not correct. You can't divide 4 grams by the molar mass of this, because that would imply you have 4 grams of the compound. You have 4 grams of carbon, which is part of the compound. So it's different. This is not correct. Unfortunately, you know, this is just the wrong approach. So what you have to do, and this is something you can do quick, you don't have to think about this for a long time. Okay? When I see a question like this, okay, 4 grams of carbon, I want to know immediately how many moles of carbon do I have. Boom, there it is. 4 divided by 12 is the amount of moles of carbon. Relate moles of carbon to the amount of compound. How much? Well, I have 4 carbons per compound, 1 over 4. That is the amount of mole of the compound times the mole, sorry, not mole mass, because I already have. You have to calculate the many moles, how many moles. So this is directly the answer. From carbon, 2 moles of the compound. A factor of 1 over 4. That's it, right? So this is an example where you just have to carefully read the question, you process that, you think, aha, carbon, grams, you never want to do anything in grams. Immediately go into moles. How many moles of that stuff do you have? Always go to moles. I have this many moles. This many moles of carbon means I have 4 times less moles of this stuff because it contains 4 carbons per compound unit. So the only thing I have to do is divide this by 4, and I have the number of moles. This is the final answer. By the way, again, if you are alert, please write this in the correct number of significant figures and in scientific notation, which was actually on the first page, in case you missed it. Write this just in the scientific notation and significant figures at all times, okay? Even if it is not asked specifically in the question to do it like that, do it anyway, because this is always correct. Scientific notation and the value of significant figures is something that is good practice you should stick to. If you stray away from that practice, you may have a chance to do it wrong, okay? Okay, another example. This is the last question, question 5. A particular reaction, doesn't matter which one, really. In this case, it is the following, where we generate sulfur dioxide. Question A says, I have formed 5 grams of sulfur dioxide. Okay? I also happen to have 1.5 moles of oxygen, which is one of the reagents. The question is, how many grams of one of the reagents do I have? Lead 2 sulfide. Lead 2 sulfide is right here. Okay? So I have to know how much of this do I need to make 5 grams of that. Now usually, in many kind of situations, what we've done is the starting amounts are given, okay? And so you calculate how many moles you have of this, how many moles you have of that, and then you can determine how many moles of the product you form. Right? This question says, okay, I can already determine how much product I form because it's given. The amount of product is already there. How much of the ingredient does there need to be to enable you to generate this much of sulfur dioxide? So in other words, I have to know how many moles of sulfur dioxide there are and how many moles of lead sulfide I need to make that. Okay? So the first thing I do, always, take this, convert this from grams to moles. You divide it by the molar mass. So this here is the number of moles of sulfur dioxide. The only thing I have to do is to convert the number of moles of sulfur dioxide to the number of moles of the reagent needed to generate that product. So I just have to look at the mole ratio, which happens to be 2 to 2, which is 1 to 1. In other words, this number here is the number of moles of sulfur dioxide, which is equal to the number of moles of lead sulfide. Okay? So there's a 2 here, 2 there. You can immediately see that for any given number of moles of this, you needed the same amount of moles of lead 2 sulfide. Then you multiply that number of moles, this is number of moles of lead 2 sulfide, by the molar mass of lead 2 sulfide, which is given here, and that's your answer. 18.7. In scientific notation, it would look like this. Okay? Sorry, it should be a 1. Apologies, this should be a 1. Go right to it. It's a 1. So, in other words, this is basically one division. This is really 1 to 1. You can see that immediately. Okay? So this is really just 1. And this is just multiplied by the molar mass. This is a calculation that you can do in principle in 2 or 3 minutes. Right? Just read it. This many sulfur dioxide right there, I can convert it immediately in moles. I know the number of moles of this. It means I know the number of moles needed to make that right here. I know the number of moles, I know the number of grams. Right? Boom, 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 boom. 3 steps that I should be able to hash out somewhat quickly. Right? Now, of course, it takes a little while to kind of get used to the question, maybe a couple of minutes. But I mean, you shouldn't stare yourself blind on what the situation is here. It's no different from anything we've done. Right? The same principle. You convert one quantity into another quantity. Okay, so keep those things in mind. I mean, another thing that I pointed out on Piazza is that the practice exam tells you quite nicely what kind of questions are going to be on the exam. Also, how long the exam is going to be, and what the relative difficulty of the exam is. Okay? This is a great amount of information for you to gauge yourself where you are at. If it takes you 24 hours to do the practice exam, you probably are not in good shape yet. Okay? You should be able to solve the practice exam in about 50 minutes. Right? And so that means that reading the question and translating that question directly into things like this becomes like a second language to you. Right? You have to learn to speak the chemical language here. These kind of conversions should come somewhat quickly after practicing all this material. All right, so keep that in mind. You will get a practice final, okay, which I will post at the end of this week. Don't do the final in the very beginning. Don't do this practice final in the very beginning, or study only off this practice exam, because that is not the right recipe. You want to use the final maybe in the last few days to test yourself where you are at. This is also why I don't give any answers. Because if I would give answers, you would go like, oh yeah, I see. Oh yeah, I see the answers. Yeah, I can do that. You don't test yourself. You don't test yourself. Seriously. It's problematic. Okay? You want to really consider the practice midterm or practice final in this case as an exam to see where are you at. Okay? How easy is it for you to solve this question? If it's too hard, you may have the same situation on the exam, right? On the actual exam. So take advantage of these services. Okay? You know, in general, this class is a primer for Chem 1A, Chem 1B, Chem 1C. You get used to the college style of education that we have, right? And you get used to doing exams in huge auditoriums where you're cramped up against your neighbor, okay? Where there's limited time and you have to show in a short amount of time what you can do. This is how we do these massive classes. This is the way we do it. So this is for you an opportunity to get used to it. I don't enjoy punishing you for anything. I hate it. I want you guys to successfully pass this class. Okay? That's my goal. My goal is to pass as many people as possible. So I hope that I give you all the tools for you to do that. These tests can only help you to point at those things that need attention from you. So consider these tests in that kind of way. Okay? The only thing you should take away from this class, don't focus on your grade right now. Forget about your grade. Focus on the material. Seriously, I mean that. Focus on the material, manage the material, process that, be able to do well, and the grade will follow that performance. Question? Say again?
I have a question about the grade.
Yes. I said don't focus on the grade. I have a question about the grade. Yeah. Okay, so you know this is okay. So the distribution 52. Last midterm was about 55 or 56. I don't know. And so the average is about 50, whatever. 50 halfway, 55. The final typically is done much better, high grades, okay? Because people really step up and do pretty well typically. So the average is going to shift up to typically about 65%. That's going to be the mean. The mean is going to determine the average grade. Okay? The average grade is between a B minus and a C plus, depending on which way the wind blows. Okay? It really depends on the kind of distribution. So sometimes it's a B minus, sometimes whatever. So that determines basically your grade. So if you are at the mean, you can expect basically a B minus. If you are significantly above the mean, you're going to be higher than a B minus. Again, it depends on the distribution. If you are consistently in the 90 to 80 percentile, you are A material. Okay? Definitely A material. If you are between 80 and 60, B-ish. Okay? And then below 60, C-ish. That's kind of like the rough scale. But again, I hope you guys don't worry about it. I know how hard it is. Because it's all about grades, it's all about the way you are relative to somebody else. Please don't make that your main objective. Your objective is try to do this material well. Your grade truly will follow your performance and how well you know the material. Even though it doesn't feel like that maybe right now, you will see in the end when your homework and your final is going to be added with the current standing, you will be at a higher percentile. I can promise you that. Okay? So all that matters is just to do as good as you can on the final exam. Okay, let's now move on because I still have some material to cover. Okay? Here we go. Redox. Who remembers that? Redox. We talked about it before in the midterm. Okay? We were actually working on balancing redox equations. And the last thing we did, we were balancing redox equations in acidic solutions. These are solutions that have a high concentration of H+. And we noticed, if you remember this, that the H+ and the H2O, the water molecules, participate in the reaction. In fact, we need these molecules to balance the redox reaction in solution. So, in acidic solution, the H2O molecules and H+ are actually part of the reaction. Oftentimes, not always, by the way, but oftentimes they are. How about basic solutions? Well, in basic solutions, there are no H+. So, what we have is H2O and OH- can be part of the half reaction and the total reaction. So we've done this already, and we'll do it again, but now we add the possibility that the reaction takes place in a basic chemical environment, under basic conditions. Okay, so what we will do is the same thing as we did before, splitting the redox reactions in two parts, an oxidation step and a reduction step, and then try to balance each of those steps. And then in the end, we'll just worry about the water molecules and the OH-, as you will see. So I'm going to give you the recipe, and then we're going to apply this recipe to a problem. Okay, so what is the recipe? Let's say I have to balance a redox reaction under basic conditions. What I do is, I use the same tools that I already applied last time. Use the half reaction method for acidic solutions to balance the equation, as if there were an excess H+. Very strange, but this is how we're going to do it. Okay, so we just do exactly the same as before in acidic solution. Okay, so that basically means that I end up probably with some H+ in my final equation. Now, evidently, H+ cannot be in basic solutions. So what I do is, at the very end of my exercise, I am going to add enough OH- to get rid of those H+. Okay? So let's say on the reactant side, there are 4 H+. I'm going to add to them 4 OH-. And then I cancel them out because all the H+ become H2O. Right? On the other side of the equation, we've also added 4 OH-. So now it becomes basic. What I do is, I generate H2O on one of the sides because I combine OH- with H+, so I cancel out the H+, generate water. So I get water molecules. If there are water molecules on the other side already, I cancel them relative to one another. And then what I end up with is the final result. Lastly, you always want to make sure that your equation is balanced in two ways. First, number of elements need to be balanced. The number of elements needs to be balanced. And secondarily, the charges need to be balanced. You need to have the same amount of charge on the reactant side as on the product side. Okay, so those are two checks that you would like to apply, and on the final, you actually will have time to do that check. Okay, so let's apply this recipe. In short, this recipe is exactly the same as we did before in the acidic solution, except at the very end, we add enough OH- to get rid of the H+ to make water, and then cross out the waters if needed. Okay, so here's that reaction. It's a very nice one. Not completely straightforward, so that's why I like to show this example to prepare it properly. So here I have a reaction of permanganate anions. Permanganate has a charge of minus, plus sulfide anions. So two anions are reacting. There are, of course, cations in solution as well. They're not given here, because I don't really do anything. They don't have any redox step necessarily. Okay, so they're not shown. So 2 anions. Then on the other side, I have MnS. Okay, this is manganese sulfide and sulfur solid. Okay, so this is an interesting situation. Why is it interesting? Because this sulfide anion, part of it is going to be converted into this, and part of it is going to be converted in that. So the sulfide plays a double role. Okay? We'll see how to deal with it. It turns out it doesn't really matter. It may be confusing at first, but if you just apply the steps, it rolls out just very nicely. Okay, so what I have to do is I just have to solve this thing as if it happened in acid, an acid solution. And the way we did that is to split this into oxidation and reduction half reactions. So let's see what is being oxidized and what is being reduced. Okay, the oxidation half reaction. Let's look. What is being oxidized? Oxidation means, what does it mean again? You lose electrons, right? This sulfur here has 2 minus, so it's negatively charged, and here it's 0, so clearly it has lost some electrons. That is an oxidation step. Okay? This manganese ion is changing as well, but as I will show in 2 seconds, it is changing in the opposite way. Because I can see this sulfide here has charged 2 minus, that means it has here 2 plus, so this manganese is 2 plus right there. Here, it has a higher oxidation state, because there's 4 oxygens, which are 2 minus. The oxidation state here is 7 plus, 2 plus here, so this one, manganese, is going to be reduced. In other words, the oxidation half reaction is the sulfur, which is oxidized from 2 minus to oxidation state 0. And the reduction half reaction is this guy, this manganese, which is going to be from 7 plus to 2 plus. Or plus 7 to plus 2. Okay? So this is how I write that down. Now, look at the following. I have to write this whole compound, okay? Including the oxygen. Because this is one polyatomic anion. I can't just split this off. This is one covalently linked unit. This thing stays as it is. This is a polyatomic anion. It can't split into separate ions, okay? Some people did that actually, again, on the midterm. They split polyatomic anions into separate pieces. You can't do that. You can't do that. It doesn't go like that. An anion is a stable species that is charged. You can't separate it into elements as if each element were an ion. Okay? So this stays as one unit. Why is this sulfur here still appearing? It already appeared in the oxidation half reaction. I need it because it appears on the product side, and this is a solid, which is one unit that I can't split. Okay? So this sulfur appears here. I have to add a source for sulfur on the other side. So it's right here. I have to list this one more time. The confusing part is I already listed the sulfur here. I have to list it again. But that's fine. That's fine. Okay? That is not necessarily against the rules. I can have just simply 2 here. One sulfur is going to associate with this manganese, and the other sulfur is going to be there. So I can easily solve that problem stoichiometrically. And it will roll out accordingly. Okay? So this is the reduction half reaction. Oh, sorry, this is the oxidation half reaction, and this is the reduction half reaction. If you look at these reactions, this looks almost balanced, except for the charges. This one, a far cry from being balanced, so I have to work on this one. So let's first look at the oxidation half reaction. Okay, so what I have to do is balance it both in terms of the elements as well as the charges. The oxidation step is already balanced in terms of the elements. That's easy. I only have to look for the charges. There's 2 minus here, there's a 0 there. Evidently, I need to have 2 electrons on that side. And that is exactly what you should have, because in the oxidation step, electrons should appear as products. We generate these guys. Okay? So, this oxidation half reaction I am very happy with. It's basically done. So let's look at the reduction step, because the reduction step is the most complicated step in this problem. Okay, so here it is. Let's look at the oxidation states. This is -2. Here, still -2. Okay? Still -2. Sulfur, when it associates with another compound, is like oxygen. And its oxidation state is -2. Manganese is 2+ here, because sulfur must be -2. So this is something that we haven't explicitly touched on, and this is why I'm telling you right here, that the sulfur here, when associated in an ionic compound like manganese sulfide, is typically 2-, like oxygen is 2-. Sulfur appears right below oxygen in the periodic table. Okay, so +2 here, 2- there, 2- there. You can see the sulfur is a spectator ion, spectator element in this equation. It doesn't do anything, it just sits there. It doesn't change its oxidation state. The thing that's changing its oxidation state is the manganese. It goes from +7 to +2. Why is this +7? 4 oxygens times -2, -8. There already was 1- there. That means you need an extra +7 to make a compound with the charge -1. Okay, so this is the setup. I have to balance first the number of elements. How did I do that? On this side, I need oxygens because oxygen sits here, but not here. I have to add water molecules. How many? 4. Okay, so let's do that. 4 water molecules need to be added because I need to balance the oxygen atoms. Okay, by doing that, I created one problem because I introduced a total of 4 times 2 equaling 8 protons. Okay, 8 hydrogen atoms. And I can solve that problem by just simply putting 8 protons on that side. Okay, so now if I check very carefully, 1 manganese here, 1 manganese there, balanced. Sulfur, 1 here, 1 there, balanced. Oxygen, 4 on each side, correct. And then finally the hydrogens are also balanced. Balanced in terms of the elements, not balanced in terms of the charges. So let's do that. On the product side, 0 charge, which means on the reagent side you also need 0 charge. But it's not 0 charge. Right here, I have a 2- here and an 8+ right there, and another minus here. Okay, so minus, that is a total of 3-, 8+. That's a total of 5+ that I need to compensate with 5 electrons. Okay, so balancing the charges required me to add 5 electrons to balance this 5+ charge in total that these components bring to the table. So now I have balanced both in elements as well as in charges. Okay. Let's take this and let's balance these 2 equations relative to one another. So let's do that. I see I have 2 electrons there in the first reaction, half reaction, and 5 in the reduction half reaction. By the way, the reduction half reaction should have electrons on the reagent side, which is the case. So it gives me a handle on the fact that I'm doing things right. Okay, so this is looking good. I have 2 here, 5 there. They need to be the same. So I have to multiply these equations with the lowest multiplier to get the same amount of electrons. So I have to multiply this by 5 and this by 2. Okay? This whole thing by 5, this whole thing by 2. And then add up those 2 equations to get to the final reaction in acid. I'm not done yet. Okay, so let's do that. I multiply here by 5, so I have 5 sulfurs, 10 electrons here. That's good, that's exactly what I wanted. These 10 electrons will cross out against one another. Okay? If you add this up, you find the following: 10 electrons on the reagent side, 10 electrons on the product side, 7 sulfurs here, 5 sulfurs there, and so forth. So the first thing I'm going to do is to cross out these guys, okay? Those two guys I'm going to cross out. And then this is the final result. You don't have to write it over again, okay? I'm just crossing out two things and following them. So this is my final result. As if the reaction would proceed in acidic solution. Okay, so 16 protons. An awkward number, right? But that's fine. These numbers can be very strange. It doesn't matter. It doesn't have to be 2 or 3 or 4. It could be 16. 16, 2, 7, 2, 8, and 5. Okay, so now I have to do the trick that if this is taking place in a basic solution, I have to get rid of those H pluses. So what I have to do is I have to add to this side 16 OH minuses. At the same time, adding 16 OH minuses to the product side. Okay, so there you go. 16 OH minus to this side. These should officially have aqueous signs, okay? They're going to cross out, so I just conveniently forgot to write them down. And on this side also, 16 OH minus, they should have an aqueous sign associated. Okay, so what I have to do now, I combine this, 16 OH minus, 16 H plus, how many waters? Yeah, they generate 16 waters, right? So I'm going to cross this part out and replace this by 16 waters. That's given over here. All right, but the only thing that I change here is I put a 16 waters in here. And now I have to look carefully. If I have already some waters on the other side, and I do, 8, then 8 of these will cross out against 16 of those. So in other words, subtract 8 from 16, and you're left here with 8 waters. Okay? Everything that appears double can be crossed out against the other side. So let me do that. I just cross out 8 against the 16, so what I left with is 8. 8 water, and now I put the phase there properly. It's liquid. Water is liquid. Water is not aqueous, okay? The water molecule becomes part of the liquid itself. So water in solutions is always getting an L as the phase. Aqueous for this guy, aqueous for all the ionic species, manganese sulfide and solid sulfur, and then this guy should also have aqueous sign, which it doesn't have. Here, but it should have. Okay? So you can put an aqueous sign right here. So this is my final result. Final operation. Pretending everything happens in acid, then I cross out the H pluses against the OH minus. That's the only thing I have to do. Different. Okay? So, since I still have time left, okay, let me check if I did everything correctly. I want to see if the charges and the elements are balanced. So there we go. Here's the reaction once again. This is my solution. Let's see if it fits. Let's count the number of elements. And let's start with hydrogen. Why not? 8 times 2, 16. 16 hydrogens. Right there. There's no hydrogens in these compounds. So 16, 16. That looks very nice. Sulfur. 7 here. 2 from the manganese sulfide. Manganese 2 sulfide, I should say. Okay, oxidation status 2. I should specify that. Manganese 2 sulfide. And 5 from the solid sulfur. So a total of 7 sulfur. 7 stoichiometric sulfurs here, 7 right here. Let's look at the oxygen. Oxygen has 8 from the water, and 2 times 4, also 8 here, so 16 total. And then from the hydroxide anions, I see indeed 16 oxygen atoms. That is balanced as well. And then finally, manganese has 2 here, 2 there. Seems to be fine in terms of the elements. What about the charges? Let's check that too. On this side, very easy. I have nothing here. 16 minus. So I need 16 minus. Let's see if I have the same here. This one is neutral. This is 2. That is minus 2. This is 7 times 2 is 14. 14 and 2 is 16. Indeed, 16 minus charges here. 16 minus charges there. Pretty convincing. This must be the right answer. Okay? This is how it works. So the tricky part about this example is, this is where I put it up. Look at the role of the sulfur. It plays a double role. That is allowed. It's fine. So don't get confused about it. Okay? Yes?
How do you know when that's the case?
How do you know that that's the case? Okay. In this case, it must be the case because the sulfur appears as a product of an oxidation step. Okay, it is 2 minus here. It is 0 here. That means it is being oxidized. That means it appears in the oxidation after. Okay? It also appeared in the reduction step because the product of the reduction half reaction contains sulfur. So I have to add it. I cannot leave it out because then I don't list the full product. The full product needs a sulfur. It's a solid. I cannot just split off one of the elements just because I find it inconvenient. No, it has to be there. Because manganese sulfide right here, that means I need a sulfide on the other side. So you keep it. You keep it on the reagent side as a source. Now, as for the oxygens and the hydrogens, we can add those by adding water and H+. Okay? But for the sulfur, you cannot say, I'm going to throw sulfur at it. You have to say the sulfur is already there from the beginning. Okay? So look at what you generate. Look at the product. The product needs an element. The element has to be there on the reagent side. But if that product also is being part in one of the oxidation or reduction steps, you have to list it there as well. And that's fine. You see that of these seven sulfurs, 2 partake in this part, and the other 5 are being oxidized. Okay? So of the 7 sulfurs stoichiometrically in this equation, 2 are not oxidized, and 5 are. Right? So that's what this equation says. So be aware of it. Does that make sense? Anybody else? Okay. Who likes this? Nobody likes it. Okay. You'll see 2 weeks from now, you'll love it. You just completely love it. This is really nice. Okay, folks, that was all.